for what are the advantages of processing signals digitally compared to what are the pros and cons of processing digital signals digitally compared to analog signals. So it is much easier and flexible and efficient to process signals digitally. So typically in most radio astronomical receivers, we try to digitize the signal as early as possible in the receiver chain. And the device which helps us in acting as a crucial bridge between analog world and digital world is what is called as the ADC, the analog to digital converter. So its main purpose is to quickly and accurately convert an analog signal to a digital sample. What you see on the left side of input to the A to D converter in the red is a sinusoidal signal, which is continuous in time. So as you know, in a computer, you will not be able to store a continuous time signal. It has to be converted to a digital, and you can only store and process numbers in a computer. So the A to D converter, operating at a specific sampling rate, converts this continuous time signal to a digital number corresponding to various amplitudes of the sine wave. So just as an exercise, what you see on the right side, there is a binary number 011 followed by that. Can anyone tell me what that binary number in what will be the value in decimal?
Yeah. What is the binary number representing? What is the value of the binary number? Huh? Girish, there are two binary numbers. Which one you are asking?
The one in blue.
The one in the blue.
Right side of the screen. 0110010 from MSB to LSB.
They are trying to work it out. Some people are trying it in mobile phone, and some are working on the paper. 114. 114 is one of the answers.
Yes, fine.
Is it, fine? Okay.
Okay, so basically, for example, if the amplitude of the sine wave here is in the continuous time can be mapped to, for example, 114, and then the numbers can range depending on the number of bits you have. Okay, like I'll go to that in the next section. So I'll just explain the process of analog to digital conversion. You basically have two steps. One is sampling. What you see in the red here is a sinusoidal signal, which is continuous in time. By sampling, what you're doing is the continuous time signals using these black lines here, where it is sampling at exact repeated intervals, you're picking up these black dots. Okay, you're converting a signal which is continuous in time to which is discrete in time. Okay, so that's the sampling process. The next step is you need to reduce the infinite range of amplitudes of these black dots and then convert it to a number where the computer is happy to process them as ones and zeros. So what it does is that is the step which is called as quantization and encoding. Okay, what you see here, analog input, and then there is this the black lines which are equally spaced in time is provided by this timing section. It operates a switch, and then capacitor gets charged, and then that particular voltage is held there for the quantization, which is converting an infinite amplitude value of the signal to a discrete set of numbers. Okay, so for example, if you have so then it calls for the physical bits of precision of a to D converter. For example, if you have 10 bits of physical bits representing analog signal, you can generate a set of numbers ranging from 0 to 1023. Okay, so that is what you see in the bottom plot here, bottom section of this plot. Okay, here. So the black dots, which contain infinite range of amplitudes, are quantized to a range representing from, for example, if you stretch the sine wave from minimum to maximum here, the minimum value of the sine wave can be 0, all 10 bits can be zeros, and the maximum value can be all bits ones, for example. Okay, so you're converted a signal which is continuous in time to a set of numbers using which we can process these signals in a computer or a processor. That is the aim of analog to digital conversion. Okay. just as a question to people there, at what rate should we sample so that at what rate should the timing signal, the sampling clock should be here for a signal of frequency having a signal having a bandwidth B? There's an important theorem there. Have you come across?
Yeah, loudly, please. Some people saying Nyquist theorem.
Perfect. Nyquist-Shannon sampling theorem. Okay. So you can go and refresh if you have forgotten about that. So if you have a bandwidth B, you typically need to sample at twice the bandwidth. For example, if it is the bandwidth is 1 megahertz, you typically need to sample at 2 megahertz so that you don't have what is called as aliasing and then corruption of the signal. So with that, we now have a brief understanding of what an A to D converter is. Then we go to the Fourier transform part. So this is the standard form where this is in continuous time. So because we have already converted the analog signal to a digital signal, we are now working with numbers. So what you see here is a discrete Fourier transform. It takes in sample X, multiplies with this complex e to the power minus j, various complex the sines and cosines. Okay, and then when you accumulate that, you get your Fourier transform. You convert a signal from time domain to spectral domain, and similarly, you can also invert it. So if these are black dots, black boxes here, what you see are 64 samples of a sinusoidal signal, and if they are fed to a FFT function, they're fed to a DFT function, and if the sampling rate was 1 megahertz, that is every microsecond you picked up one of these boxes, and then if you collect 64 of them and then pass it through this discrete Fourier transform, then you will be able to get the input tone at 46.875 megahertz. I know that I'm just trying to give you a flavor, a feel for this. Maybe we can discuss more later. So you'll be able to transfer that sinusoidal signal in time domain to frequency domain, where you have a tone, where energy is only at the frequency at which it is supposed to occur here. Okay. So DFT is an inefficient way of implementing the Fourier transform in a computer. So obviously, most of you, I'm sure most of you would have heard about fast Fourier transform, FFT, which is a computationally efficient algorithm to compute DFT. So DFT through FFT is one of the primary tools of digital signal processing. So please be aware of that. So this was the F engine in the earlier block diagram, which transforms signals from time domain to spectral domain, not just a tone or a sinusoidal signal. If you have a signal which is noise-like and if it is band limited, you can sample it appropriately and then pass it through this. You will get back the power spectrum in the context of the digital receiver. Okay, so now that we have A to D converter, we know about FFT, and then we know about multiply and accumulate, which is the correlation part. So we put these A to D converters and the device called field programmable gate array. I'm sure Vani would have given you a feel for this, what it contains. Just to refresh, it is an integrated circuit designed to be configured by a customer or a designer after it is manufactured. Hence the term field programmable. It contains millions of programmable gates, logic gates, say a lot of memory, what we call as block RAM, and then specialized modules like multiply and accumulator unit, and then high-speed interfaces, and various things to implement complex digital signal processing algorithms in real time. So when you put ADCs and FPGA together on a printed circuit board, we produce what is called as a digital signal processing hardware platform. So this is one platform consisting of two ADCs, one Vertex 6 FPGA from Xilinx, which we put together. This was designed and developed at RRI. It's called PSPEC. So on one, the A to D data coming from ADCs after digitization is grabbed by the firmware inside FPGA, what you see here in this block. And then it is Fourier transformed and correlated to generate power spectrum. The power spectrum streaming out of, for example, a 1 gigabit Ethernet interface is interfaced to a laptop for data acquisition. Okay, so this is how we implement a hardware signal processing, digital signal processing hardware platform. Any questions here?
Any of you have questions, please? Doesn't seem to be any right now, Girish.
Okay, fine. We can take it later if there are. Okay. So next we move to, we have designed, developed and tested individual subsystems like antenna, analog receiver, digital receiver, data acquisition, processing pipeline, everything. And then we have put them together, and in the integrated form, we have tested them in the laboratory. And then how do we take it out to the field? And then, so can we do this in Bangalore, for example, at RRI? There's no way we can do that because we need, there's a lot of radio frequency interference in Bangalore in the frequency range in which we operate, that is from 40 to 200 megahertz. Radio frequency interference can roughly be defined as an interfering signal which causes contamination of data, and the receiver may not behave like the way you expect it to be. Okay, so there will be contamination of data. This is the data, this is a signal which was not intended for us, because an antenna will not be able to differentiate between signal which is coming from a celestial source and a signal which is man-made, for example, coming from a FM station or any other interference, airport radar or walkie-talkie or any of these things. Antenna will not be able to differentiate. It is any electromagnetic signal, it converts it into electrical signal, and the rest of the system amplifies it because it doesn't know. Its job is to, any signal within the band, it will process that. So the receiver may not operate in the way that we have designed if the signal is too strong, and it can contaminate data. So that is what we call as radio frequency interference. So we want to avoid that, because it is already extremely challenging to detect a weak signal, which is tens of hundreds of millikelvin, the EOR signal. And in the presence of already large foreground, Saurabh referred to this, and then you require 1 part in 10 to the power 6 dynamic range. In addition to this, if you have terrestrial man-made radio frequency interference, which can be more than this 10 to the power 5, then it becomes very difficult to operate. Some of the typical sources of interference is, because we are operating from a frequency range 40 to 200 megahertz, FM sits right in the middle of the band. For example, Bangalore has some 7 or 8 FM stations and very strong. So it will kind of saturate the receiver system and will not be able to observe. Other sources of interference is various communication, airport radar, for example, walkie-talkie, police communication, emissions from satellite. Emissions from satellite, like you'll see, even if you go to remote sites, you can't escape that. And then certain lights and lamp sources, which I will show you, also generate, they have a lot of switching signals, and they generate a lot of interference, and sometimes, band is totally distorted. So these are the typical sources of radio frequency interference. One that you see in red is another source that which is unavoidable. It is something that is generated by our own electronics, mostly digital electronics. Digital electronics is noisy because you have a lot of clocks and switching signals. Clocks, its harmonics, switching signal, their harmonics, and then they spread across the band. So we take special care in trying to control these signals which are generated from our own sources, so that they don't go out, leak out from the digital receiver, reach antenna, and then get into the receiver chain. So once it is there, there's nothing much that we can do. So we take special consideration. I'll tell you about that. So now you understand why we need to go to a radio quiet site. So typically we identify remote locations. By remote locations, what we mean is where we are far away from civilization, typically where population density is very small, and then remote, undeveloped, developed places, or where kind of even bordering forest regions and other things, so that we can escape from all these electronic devices from surrounding places, and then FM stations and various other things. So that's the need for radio quiet observing site. And then just because a site is remote, it doesn't mean that it is radio quiet. We'll see that. So in our pursuit of finding a remote site, we went to Andaman and Nicobar Islands once, and then about 30 kilometers from Port Blair, Sri Vijayapuram now. And then we deployed our RFI recording system. Okay. So this title of the talk was about SARAS at various latitudes and altitudes. So please keep an eye on the latitudes. Okay. So we were about 25, 30 kilometers from Port Blair on this route, to reach northern portions of northern tip of Andaman Islands. Okay, so when we tried to be there, and then population density here, like a population of Andamans is about 4.5, 5 lakhs or something like that, and most of them live in Port Blair and big cities like Mayabandar and Diglipur. So density is about 46 persons per square kilometer. Just for reference, it is 10,000 plus persons per square kilometer in Bangalore. Okay, so now you can appreciate why we want to go away from. So wherever there are people, where there's civilization, obviously there's more electronics, more interference signals, more electronic facilities, TV, radio, and other things. So we want to be away from civilization. Okay, so this place, which was about 30 kilometers from Port Blair, we set up our instrument. Everything was fine except for a couple of interference signals, which was okay. The system can manage and operate despite them. Okay, so just as it got dark and the nearby a big lamp post, they switched on the lamp post. The band, what you see when lights off, you can see what happened in lights on across the frequency range of interest. This is from 5 megahertz to 500 megahertz. Entire band was unusable. Okay, so just because a potential site is remote, it doesn't mean that it is RFI quiet. So we need to carry out a radio frequency characterization across our band of interest, or slightly even broader, wider than our actual band of interest, in order to be sure that our systems can operate safely and the way it is intended to work. So what we did was we moved to a place called close to Diglipur. It's a dam in close to a forested area. Okay, we shipped all of our radio frequency equipment. You can see a picture of this here. This is the RFI antenna, and then there's the preamplifier and the 10-meter cable, and post amplifier and spectrum analyzer and a data recording system, which is kept inside this RF shielded enclosure. Spectrum analyzer and laptops, which has clocks and switching frequencies, we do not want them to we did not want interference from them to leak out, get to the antenna, and then come back in the receiver chain, so that we'll not know whether it was present in the environment or it was our own self-generated. So what does this black box here do is, it is called a RF shielded enclosure. It prevents signals from leaking out. It heavily attenuates. It cannot prevent it fully. It heavily attenuates, typically by about 70, 80 dB. By which time it will be very weak to be picked up by the antenna and then the rest of the receiving chain. So, and then because you're in a remote place, everything needs to be powered by batteries. We carry them wherever we go. So the receiver system, RFI recording system was set up, and you can just see the plot here from the spectrum analyzer screenshot, except for this particular radio frequency interference, which is at 137 megahertz, which is a satellite coming from what you call as OBCOM satellite. The rest of the band was pretty clear compared to this place. You can see how bad it was. So now you appreciate why we need to be really far away from settlements and urban areas. Okay, so we did a thorough characterization. And then just for reference, we have what you see here is called as a waterfall plot. Okay, where x-axis here is frequency from I think 50 to 500 megahertz, and y-axis is time, where spectrum is recorded from 50 to 500 megahertz and acquired for a long duration, and everything is put together here, what we call as a waterfall plot. Compared to Gauridibanur, like you see, where especially at low frequencies, where there are many contaminants, including the Bangalore International Airport, which is close by, all those things are absent here. More or less, the signal strength is at the levels of at very low levels. So we are happy to be in a place called Kalpong Dam. Any questions?
Yeah, please.
Yes.
Yeah.
Yeah.
Sir, at 50 megahertz, what is that strong signal that we're getting here?
Yes. So this 50 megahertz, we really clearly do not know what it is, below about 40 megahertz, more or less anywhere in the world we go. I think we have sampled some 4 or 5 places, including the present place in Svalbard. There are these very strong lines at very low frequencies. Maybe we suspect some of them, especially here in Svalbard. We think there are some ionoson experiment which is regularly done. And then also, let us not forget that this is the frequency range in which we have our shortwave communications. So, like for example, all of us at some point of time, maybe we would have tuned into BBC. So obviously, it comes to India all the way from wherever it is, maybe with repeater station or whatever it is. So low frequency is really contaminated more or less anywhere you go, up to 40 to 50 megahertz. Okay. So it can come from somewhere else where it will not necessarily be locally generated, but here in Ny-Olsen, it is locally generated, we are sure. Any further questions?
Any questions, Karan?
Yeah, and then just to answer the previous question. Typically, our frequency range of interest is beyond this 40 megahertz, 40 to 200 megahertz. So we put nice sharp filters so that the strong interference can be attenuated heavily, and then it doesn't, most often it doesn't cause any contamination of our data. That's the way we handle this.
Thank you, Girish. I think currently the answer seems to be fine for them.
Okay, fine. So this was about the site in Northern Andaman and Nicobar. So the next place we go is to Ladakh, and then it was a place in what you see here in red here. This is the Hanle region in Ladakh. We were only about 30 kilometers from border here. And then again, population of Ladakh is very small, and then 46% per square kilometer in Andaman and Nicobar is reduced by 10th to 4.6% per square kilometer, and you expect things to be great, but many times it turns out that it isn't for various reasons. Like what you say again, a waterfall plot from 50 to 500 megahertz. There are interfering signals coming from here. And especially after Galwan, there's been a lot of other developments, which is making it very difficult to operate SARAS, the very sensitive SARAS observation, to carry out very sensitive SARAS observations in Ladakh. So just because the site is remote does not necessarily mean that it is suitable for SARAS experiment. Okay. So then the National Center for Polar and Ocean Research, NCPOR in Goa, which operates under the Ministry of Earth Sciences, they had a call for proposals in 2023, saying that if you want to conduct any of your experiments in this place called Svalbard, it's an archipelago, number of islands put together. Norway operates the place. It is owned by Norway. And then we submitted a proposal, and then Saurabh presented our case there, and then it went through a peer review process, and we were selected for radio frequency characterization of a site in the place called Ny-Olsen in Svalbard. I'll tell you more about that place. Okay, so we were selected, and then plan was to bring our RFA recording setup to this place, and then do a frequency characterization and assess its suitability for SARAS deployment in Ny-Olsen. Obviously, we are here. It means that it was reasonably good. That's why we are here. So the way we reach Ny-Olsen, the way we reach Svalbard is you fly from India to Oslo. So you typically take a Schengen visa for that. And then from Oslo, you fly to Longyearbyen. Longyearbyen is the capital city of Svalbard. Okay. And then please have a look, keep an eye on the latitudes here. Longyearbyen is roughly 78 degrees north, and Ny-Olsen is about 79 degrees north. For reference, Bangalore is roughly 13 degrees north and 78 degrees east. And this Svalbard region is 11 degrees east because we have moved west relative to Bangalore. Okay. So although Svalbard belongs to Norway, it is not part of Schengen area. So before you exit Norway at a place called Tromsø, you need to get your passport stamped saying that you are exiting Schengen area. And then from there, you fly to Longyearbyen, which is about 1,200 kilometers, 1,000 kilometers, something like that. Okay. So from Longyearbyen, we need to go to a place called Ny-Ålesund, which is here. And this distance is approximately about 100 kilometers. Ny-Ålesund does not have a regular commercial airport. It has a small airport. Okay. So we need to fly this, we need to take a short flight from Longyearbyen to Ny-Ålesund.
And if they are losing you for a while, you didn't see the first stop in a very less.
Okay.
Yeah, last 20 seconds or so, we were not able.
Okay, I'll repeat it. Okay, so just to summarize, we need to finally reach this place called Ny-Ålesund. That's where I'm coming to you right now from. Okay, and then Longyearbyen has a regular commercial airport where you regular Boeing and airline other things can operate. Whereas Ny-Ålesund has a very small airport. Okay, so you can't fly using regular commercial airlines. Okay. So what we do is from Longyearbyen, we need to take a charter flight from Longyearbyen to Ny-Ålesund. This is the picture here at the bottom left, where we are all inside the this Dornier 228 aircraft, and um, in the nose of the aircraft, all our laptops, spectrum analyzers, and various sensitive equipments were kept here. And our personal baggages and even the SARAS equipment were loaded. SARAS equipment reached much before we reached Ny-Ålesund. They load all the other baggages through this door, and then we enter here. It can carry about 14 people in one go. Okay, so this is an interesting part. Okay, so just to give you a sense of time there, it was around 10 o'clock when we took off from Longyearbyen, and it was about 30 minutes. Fine. Okay, I'll just summarize quickly. We have reached Longyearbyen, and from Longyearbyen, we need to fly to Ny-Ålesund, which is northwest, about 100 kilometers. And like I mentioned, we don't have regular aircraft, commercial aircrafts there. We need to take a charter flight from Longyearbyen to Ny-Ålesund. Okay, this is the flight Dornier 228, which flew us from Longyearbyen to Ny-Ålesund. Okay, and then this bottom left is a picture of the four of us who were traveling. And then this is me, Saurabh. This is Vipin Das from NCPWR, and this is Yash, Saurabh student. Yash is here, and then this is the three of us in front of the Dornier aircraft before we left Longyearbyen. Okay, so I just want to share what I wanted to tell you is it was around 10 o'clock in the morning when we left Longyearbyen. Okay, and then in about half an hour's time, around 10:30, 10:35, we approached Ny-Ålesund. What you see here is the Ny-Ålesund settlement. Like you see, the entire place has artificial lights, and around 10:30, this is how it looked. And then I'll just play this. This is the Ny-Ålesund harbor. This is the settlement, and this is the airport. Okay, I hope you like that. It was just to show that it was pretty cold and dark when we landed in Ny-Olsen, even though it was 10:30 a.m. We were still in what is technically called polar night when we landed here on February 6th. Okay, and then just to orient yourself on the map, this is where we are. This is Ny-Olsen. This is Longyearbyen, capital of Svalbard, and we are just about 1,280 kilometers from North Pole. Okay, so we are in Svalbard, and this is the kingdom of the polar bear. There are some interesting facts about Svalbard. There are more polar bears than people. Entire population of Norway is of about 5.6 million. Most people live in either Oslo, Tromsø, or big cities. There are very few people beyond this place. Ny-Olsen in Svalbard is one of the world's northernmost permanent settlements. India has its research station called Himadri in Ny-Olsen, Svalbard. And then civil polar night lasts from middle of November to end of January. Svalbard's midnight sun, Norway is called land of midnight sun, lasts from middle of April to end of August. We are now slowly, from the time we came here from February 6th to 21st of February, we can, I think I'll also try and come to you live with live pictures if possible. So we can see slowly it's getting there's more light every day as we start moving towards March 17th, when the sun is expected to be up and shining here. We only see light here, but we don't see sun as of now. Okay. So that's about Svalbard and Ny-Olsen. And what you saw from that aerial view, it was this place which is covered with snow, or it was covered with snow, and then there were artificial lights. This is a picture which is taken during a different time, probably during polar day. You don't see a lot of ice in the settlement. This building here is Himadri, that is India's research station. And then what you see here in this blue is the world's northernmost post office. This is one of the first buildings to come up in Ny-Olsen. And then there are many countries have their own research stations. Italy station, and then this is from the Norwegian station called Norwegian Polar Institute, and there's something called AVIPEV, where the German and French people operate that station and then carry out their mostly climate and atmospheric studies, which happens here. And then please remember this service building. This is the most important building in Ny-Olsen, apart from your scientific activities. Okay, that's where we gather for our food and any social gathering. Okay, and then there is the harbor. During summertime, cruises come here. People are not allowed to stay for a night here. They can come here, and then there is a shop. They can shop for souvenirs, and then they'll have to leave the place. You can't stay in the place. So also remember there is a gymnasium for people who stay here, so that you can work and keep yourself fit. And this is Greenland Sea. This is called fjord, FJORD. So this is part of Greenland Sea here. So this is about the settlement, and this is about the settlement. So what you see here in yellow block is in a yellow dashed line here. This is the settlement, roughly about 1.5 square kilometers or 2 square kilometers. So if you are moving out of this safe zone, you cannot move out without firearms. The reason is what you see here. This is our station leader. Every station has its own station leader. This is Sarabjit Singh, who is on the other side of the room here from where I'm coming to you. Thanks to him, he brought me here, without which I would not been able to come to this place called Gruebada lab here. Otherwise, I had to present this from Himadri. If I was presenting from Himadri, I would not have been able to show you the receiver systems, which is just behind me here. Okay, so just before we left the safe zone, that is the settlement, Sarabji, the station leader, had to load his gun, and then he has to carry this rifle and a flare gun for, as you can see from the picture here, polar bear danger. You can't exit this safe zone without having a firearm and a flare gun. Okay. So with that, I'll just go back to this is the settlement area. If you are moving beyond this region, you cannot walk out of this region without a firearm protecting you. Okay, so the place where SARAS 4 is currently installed is near this place called Gruvebada Lab. Part of the receiver is inside the lab, and the antenna and analog receiver is outside, about 100 meters from the lab. I'll try and show you some videos of that. And Gruvebada Lab is about 1.25 kilometers from Himadri. Okay, this is just to orient you. So, like Prabhu mentioned earlier at the introduction, I was here in Ny-Olsen in 2023 with the RFI recording setup. RFI antenna was set up above the place where I'm currently sitting in the Gruvebada lab rooftop. And then this is the same place from where I'm coming to you from right now. It's the same room where the RFI recording setup was, the backend recording setup was also placed here. Okay. So how did the compared to, for example, sorry for only taking GBD as reference because that is something that we are familiar with. Compared to GBD, when we did a RFI characterization of the Ny-Olsen area, we found that there are a lot of interference lines in the low frequency, SARAS low frequency band, but 100 to 200 megahertz appeared clean, except for 172 megahertz. In addition to carrying a firearm and a flare gun, you also need to carry walkie-talkie when you are out of the safe zone, that is the settlement area. Because in case of any emergency, you can contact. There's always going to be security 24/7. You can request for any help if your vehicle breaks down or if you have any other issues. They can help and they can try and rescue you or help you, whatever it is. So you always carry walkie-talkie. And everyone who's going out of the settlement area for their experiments carries walkie-talkie. And so this frequency range around 172 megahertz is you have this walkie-talkie communication, which is something that we cannot avoid. Okay. So, but for that, 100 to 200 megahertz was really very nice for SARAS. That's why we are here with our SARAS equipment, the entire radio meter. And to answer one of the questions that came up earlier, what happens at low frequencies? Like you see, there's ionosound experiment, which is happening in a coordinated way between Svalbard, Norway, Sweden, and Finland. That's what we understand. Okay. So I'll now let you know some of the challenges that we encounter wherever we go. And not that you don't have challenges when you go to place called Andaman or Ladakh. So typically for SARAS low band receiver, that is 40 to 100 megahertz, typically it is deployed on antennas and analog receiver is put in a raft, and then the raft is deployed on water, from the picture that you see on top right. And then analog signals are converted from are transported over fiber, RF over fiber, and then what you see in the bottom middle part, this is the correlator tent, and then inside this tent we have analog backend receivers which will convert optical signals back to electrical signals, and then do a signal conditioning, amplification, and filtering, and then that is fed to correlator, which is shown with door open on the right here, on the bottom right picture. And then here is a colleague, Adarsh, who is trying to see if the entire system is, after deploying the raft on water, if everything is functioning before we get observations. Okay, so everything was ready. Typically, SARAS observations are carried out at night. Basically, we want to avoid the radio's emission from sun, and also that is when by around 9:30, 10, even if there are surrounding people in the surrounding areas, villages or something, you expect them to settle down for the night, and then you have minimum interference. So that's why we operate SARAS later in the night, say typically from 10 to 5 a.m. or something like that. So when we came back, when we were coming back to start SARAS observations, especially in Andaman, we had a lot of the snakes that because it had rained in the afternoon, they had come out of their holes there, and this was a challenge. And then this guy, Andaman pit viper, maybe he was interested to know how correlator works. He was right next to the correlator. And then on the bottom left, what you see is an giant Andaman centipede. Um, uh, he would always welcome me after we began SARAS observation, and then I came back to the guest house. This guy would be there to welcome me. And then finally, I figured out what route it takes, and then put duct tape so that he couldn't come inside. So, in addition to technical and scientific challenges, we will also have such challenges which are manageable. Okay, that was the challenge with Andaman. The next thing is I'll also give you a feel for what kind of challenges we face in Ladakh. Here you see top left picture, you see that some of us are trekking there at this high altitude, 4,800 to 5,000 meters. Just for reference, Mount Everest base camp is about 5,300 meters, so very close to that. So it is definitely challenging to be doing these things there for people like us who come from about 1,000 meters. Bangalore is 980 feet, 3,000 feet above sea level, about 1 kilometer above sea level. Okay. So again, there is wildlife. Maybe this is more of a domesticated one. So these thing, and there's something else called kiang, the local horse/donkey, whatever they call it. So we are always concerned that they will step on our optical fiber. So hopefully they have never damaged anything. But we are not as lucky as we were in Ladakh when we came to Nai Olson. I'll let you know why. And then in addition to that, because this was SARAS low band, that is 40 to 100 megahertz, we had to deploy this on water. In addition to trekking or something, we also needed to row a boat to deploy this at 16,000 feet. So these are some of the challenges. Nature has its own way of compensating for us. We get to see these such wonderful rainbows and sceneries in Ladakh, especially as we travel from the site to our base camp. I did not say much about this. We have nothing to do with COVID with this pulse oximeter. The reason is all of us keep checking this at regular intervals because, as you can see from this plot, at a level of 16,000 feet, 4,800 meters, oxygen content in the atmosphere is less by about 50%. So as soon as we reach these places, we can feel that our heart is pounding, trying to get the required oxygen supply to keep everything functional. So this is a huge challenge. And then typically we need to get used to these high altitudes, what we call as acclimatization. And then we always take it slowly. Every 1,000 meters that we go up in altitude, we rest for a while and then get used to that and then go higher up. Okay, so that's how we manage this challenge. And again, SARAS was deployed, and then for the first couple of days, we really did not have a good road from the site back to the base camp in Hanley, which is operated by the IA Observatory there, the guest house there. So for a few days, which was wrong on our part, we decided to stay at the campsite, either in the tent or sitting in the vehicle. So it was challenging to be there at that altitude and cold, but you are always rewarded with wonderful sunrise, sunset, everything. So we think SARAS is the only CDEOR experiment in the world that has been deployed at such a high altitude. Okay, so that was about Andaman, challenges in Andaman and Ladakh. I'll just play you a video of how I saw Gruvabada when I visited this place first time in December of 2023, where we were right in the middle of what is called as the polar night. So just try to see, and then please remember this video, because I'll also play a video of from the same location as we see it in the present visit. This is from rooftop of Gruvabada, and what you see there, lights are the Nai Olson segment, And as I pan left, you see the airport. The lights are coming up there. And then once I'm panning it beyond the airport, it's interesting. So you can see that it is pitch dark. For some reason, if the artificial lights were to go away, then it would be pitch dark. You can't see anything. We are bang in the middle of polar night. I'm actually panning. You almost see nothing. And that is the observatory called Zeppelin Observatory, which is on a mountain top. I'll show you a better video of that. And as I almost complete 360 degrees, we'll start seeing the Niall-Olson settlement once again. This was in polar night, the middle of polar night. Okay. For those of you who are assembled in GBD, what do you mean by polar night? Any idea?
So, sir, when the electromagnetic field line of sun interact with the magnetic field line of Earth, they create some because of that interaction, there's a creation of light called as polar lights or aurora borealis.
Okay. I mean, you answered the question which I wanted to pose a couple of slides later. That's okay, fine. But what is a polar night?
Question is polar night.
I thought polar lights.
I think the answer came for your next slide, I think, right?
Yeah, the answer came for my next slide. I don't know how she got to know about my next slide.
Okay, what is polar night?
6 months of night.
That I thought like lights.
No, don't worry, but polar.
No, fine. No problem. You answered my next question in the next slide. No issues. Okay, fine.
Anybody to answer address what is polar night?
Basically 6 months of
4-5 months. Yeah.
around 5 months or 6 months of night, and the other part of the year be the day. So that night is polar night. 6 months of night.
Okay, great. You are very close. Okay, I'll just tell you why it is. Okay, so right definition of polar night, which is opposite of midnight sun, is when none of the sun's disk is visible above horizon at all. So it only happens within polar circles in the north and south. And as you see here, as you can see from the picture here, sunlight doesn't reach this place at all within the Arctic Circle. Okay. That's the reason why there is no sunlight at all for about 4 months, 4.5 months. And when you don't see sun's disk at all in the horizon, so that is when it is called polar night. And as you can see from here, in the northern hemisphere, September to March is when typically you don't see the sun's disk at all. It doesn't appear. And at the same time, polar night in the southern hemisphere is between March and September. Okay, so one is the northern hemisphere is for Arctic, the other one is for Antarctic. Okay, fine. So the reason why we have this is because of the tilt of the Earth, and as Earth goes around the sun, like what you can see from the right side of the picture here. So if this is December, that is when I was here last time. It was in the middle of polar night. And right now we are moving along this circle and then somewhere very close, somewhere in between. So we are about a month away from March 20th, when the sun is around that time when the sun is expected to show up above the horizon completely. Right now, I think from some of the instruments here, we can see that sun's disk is only about 0.1 or 0.2 degrees, 0.4 degrees above horizon. So slowly as time progresses, sun will start coming, more of the disk will be visible, and then the entire sun will be visible at some point, sometime during mid-March. Okay, so we are moving along this red line here currently. Okay, so that's the reason why we don't have sunlight during polar night. And then when you come to summers, you'll have 24/7 sunlight. Sun almost never sets. So if that was the challenge that we faced when we were doing the carrying out a frequency characterization of the Niall-Olson settlement to assess the feasibility of deploying SARAS. Okay, So some of the challenges that you face due to polar night and the pitch dark and other things, the nature compensates you by, this is what we got to see when during the auroras. The question that one of the students answered, this is the kind of auroras that we got to see from New Alcyon settlement and Gruevada. Okay, so it was fantastic. Curtain of lights hanging from the sky, and then they're fluttering, and then mostly green here. So, well, that was from the December 2023 trip. And then even this time, even a couple of days back, we got to see fantastic auroras thanks to Yash. Oh, sorry, I have missed the A. Yes here. Yash Agarwal, Saurabh's PhD student, who is with us here, like you saw the picture. So he managed to capture a couple of fantastic auroras as we were walking back from Gruevada to Himadri one late evening. Okay. Like I said, we are slowly coming out of polar night region. February 18th is when the sun was 0.1 degrees, sun's disk was 0.1 degrees above horizon. So because of that, there is some light during this trip, maybe around, at least when we came by about 11:30, 12 o'clock, and then for a few hours, and then it would get dark again. So I had not seen this during my 2023 visit. This is how the settlement looks in sunlight. And this is the three of us in front of this. And then this, the bottom left, is the view of New Alcyon settlement from Gruevada. Okay. And this is the Gruevada lab. What you're seeing is the entrance. This is the rear side of Gruevada. And then the light you see here is where the analog backend and digital backend receiver systems are presently kept. This is the same room from which I'm coming to you live. And then about 100 meters from this is where this antenna and analog receiver mounted on a raft is placed. And as like in the SARAS low band experiment, RF is transported to the place where digital and analog backends are kept in this room here via RF over fiber. And then our friend here, this Arctic Fox, got interested with what experiment we are doing. So he found this to be interesting, and he chewed it, and then he rendered the cable, some parts of the cable not usable. So we were finally able to manage to get the rest of the cable working, and then did a small reconfiguration of the analog receiver, and then finally got going about 4 or 5 days back. So this is the last thing that we expected in a remote place like this. We had initially asked for conduit through which we could route this optical fibers for safety from snow and from these wild animals. But at that time we couldn't get it, and now we have managed to get some conduit of about 90, 100 meters length, and we have laid them out, which I'll show you later in my video. So just to suggest that every place comes up with its own challenges. And then here, at the time we were deploying the analog antenna and analogs with the raft, there was knee-deep snow, and then we had to carry this analog receiver, which weighs roughly about 25 kgs. We would take turns to carry them, and then we had our own ways of trying to move them from Gruevada lab to the site where it is now currently deployed. So we'll just conclude with move to the last section, which is life in the Arctic region. So we stay in the place called Himadri, which is India's research station. There are about 4 rooms here in the first floor, and each room can comfortably accommodate 2 people. At any point of time, 8 people can stay here. And there's a computer lab where we all sit and work. And then there's a lounge for visitors, or we can sit here. And then somebody who wants to be away from this place where the 7 or 8 people can come here and work. And then there's a small kitchenette where we can make tea, prepare tea. We're not supposed to cook. And then That's how the Himadri station is. And service building, I told you that we are, it's very important place. This is where we all people who are staying in Olsen, they all assemble here at fixed times for food and for social events. This is how I saw the service building in 23rd during the previous visit, and this is the way I saw it during my present visit. Are there any questions, Prabhu?
Girish, I think I'll ask just hold on. Any question? We are hearing your voice and then we are hearing your voice. So is there any questions you have? No, you both clarify. Okay. No questions right now, Girish.
Right now, okay. So then how do people keep, because it's always cold, and how do people keep busy? There's plenty of facilities. There's a gymnasium, there's a sauna, massage chair, and then people go skiing. And also weekends, typically people take off, they move away from the settlement, and then they stay for the weekend in what we call as cabin/wilderness hut. They carry food and then they come back only by Monday morning or something like that. So they have their own way of keeping themselves busy and active and fit. So how has the weather been, Olsen, from the time we came here? Average temperature is around minus 13 degrees, and one second. Average temperature has been around minus 13 degrees. And obviously you expect a lot of wind here, cold winds blowing, and then so it feels like an average temperature. Typically every day we would feel like it is minus 22 degrees due to wind chill. So I briefly refer to this. February 18th is when the sun was slightly above for the first time. As you see here, down and doesn't rise. February 18th is when sun was part of the sun's disk was visible for the first time. And then how do we manage to be working in the cold and then when you're out in the field? So the only way to do that is having multiple layers of clothing, warm clothing. And then as there's a popular saying in Scandinavian countries, there's no such thing as bad weather. It is only bad clothing. So whether you know that weather is going to be challenging, so you better be prepared. That's what it says. And have the required gears so that you can go out in the field and work. So multiple layers, that's what we do. But because I'm right now in Weather lab, where there are plenty of heaters around, that's why I'm in my t-shirt. So as soon as I step out of the building, I need to layer up and have multiple layers to protect myself. Okay, so I think I'm at the end of my presentation. What I'll leave you with is this is what you see just outside Weather lab. This is the settlement. Again, a panoramic view. Like I said, you can just see some sunlight hitting the top of the peaks of the mountain there. And then that's what you see here. And then this is the Zeppelin Observatory, which is on top of this mountain here. Okay. And then it is basically to study for atmospheric studies there. And then people reach that place through a cable car. And then as I pan left, I'm showing you the eastern part of the sky where it's simply coming alive. And this is the Weather lab from the front view of Weather lab. And I'm also showing you the room in which I'm right now sitting. It's the last room here at the back. This one. Okay, so that was Weather, and now there's the next video where I'm entering Weather lab and also showing you the receiver system, the backend analog and digital backend receivers which are set up inside the Gruvavada lab. There's Saurabh there. It was just after his talk 2 days back. And there are many experiments going on here from various institutions from India, Indian Institute of Tropical Meteorology, Indian Institute of Geomagnetism, BARC, and various other places. Number of experiments which are going. And we don't know how much of these is contributing to the low frequency interference that we saw earlier. And this is exactly the place where I'm coming to you from, live from. And this is our digital receiver, this white box. Again, a shielded enclosure I referred to earlier. Okay, digital receiver is housed inside this so that contaminants, clocks, rate, and other harmonics and switching signals, they don't leak out from the digital receiver, digital electronics, and reach the antenna. This is the analog signal conditioning unit. And this is the optical fiber, which brings RF from the antenna there, which I'm now trying to zoom in there. And then the optical fibers are routed through this red conduit there. And control signals go from digital correlator to switch the states within the analog receiver. So it's a two-way communication. Okay. So the next one is I'm trying to take you to the rooftop of Gruvavada. So then I'll soon climb the icy ladder there. It's very slippery. Need to be very careful. Again, you see number of experiments which are ongoing. Plenty of equipment has been installed on the rooftop. Sorry for that. You will see a lot of noise. Which is me moving on ice here. Okay, so this is the view of the raft containing antenna and analog receiver and the optical fiber, which is entering the back-end room. You don't see antenna because antenna is covered with the yellow silpoline sheet that is to protect it from, because it's very windy, from snow and wind, slow accumulation on the antenna to protect it from that. And that's the eastern part, which has just come alive in the last week or so. That's an Olsen settlement. That's where in one of the buildings is the Himadri station. As you expect, it is snow everywhere. Okay, that's a Zeppelin Observatory again. Okay. Fine. I think this is all I had to show you. Tack for tiden din. In Norwegian, it means thank you for your time.
Girish, ಧನ್ಯವಾದ Girish.
Oh, thank you. ಧನ್ಯವಾದಗಳು.
So, any questions for Girish? Yeah, there are some questions, I believe. I think the first one, you please tell your name and ask the question.
Okay, my name is Arshia, and I just wanted to ask during nights of high auroral activity, what do you do to protect your instruments? Like, do you shut them off, or are there any other precautions, or is that not really much of an issue anymore?
Okay, nice question. Obviously, during nights, at some point, you expect auroras to peak or something like that. Okay, and then we understand that they are not emitting frequencies which are strong enough or something like that in our band of interest, that is 100 to 200 megahertz. So in a way, it doesn't affect us.
Any other questions, please? Any other questions? Any other questions, online participants? Yeah, there is one question here. Please come. Tell your name and
My name is Girish. I am asking for what is the frequency range for radio television?
Again, that falls in the earlier terrestrial communication was around 170, 174 megahertz. And then these days, satellite communication, your dish TV, it operates at a few gigahertz, and they generally don't affect us, to going up to maybe 170, 180 megahertz.
yeah, the UHF band may even go high, I think. Rangiraj may be able to tell us. Girish, today we have a very special visitor. Can you stand, please? Finish. I think your question is not yet answered fully, I think. Do you have further question? Rangiraj, what are the TV station frequencies?
Now this analog transmission is over.
But what used to be?
Up to
I don't know. Girish, are you able to see Rangiraj here?
Hey Girish, hi.
Hi.
340 megahertz UHF.
But the VHF.
Yeah, VHF is 150, 170, and so on. But that is gone now.
Okay.
We do direct cable transmission, so digital lines.
Yeah, it's okay. My recollection is television bands used to start somewhere around 55, 65, 60 megahertz. Okay.
All the way to
Some 800, 600, 700 UHF band.
VHF band.
Yeah.
The VHF band goes up to 200 something. And that is all gone now. Nobody does analog transmission.
Unless some very old station in some countries operating. Bangalore TV is still operating.
But that is digital transmission.
No, still analog. Yeah.
Wow.
Okay. And they are more likely to move to
VHF. VHF.
Only the government television stations are operating in that band. So the band of their interest, most likely in that country, I think may not be anything in the.
No one gets radio TV transmission.
Most likely,
Bears that much
did not have.
So we don't have interference from television transmission in Nielsen, not in the terrestrial thing. Maybe there is DTH. So we don't find any interference around in the 100 to 200 megahertz band that we are right now focused on.